will talk about bias in meta-analysis, and the key issues here are publication bias and funnel plots, and we will use or show you the trim and fill method for dealing with this, and also some of these funnel plot tests. So these are keywords you may have heard of before. So as for all types of studies, there are lots of biases also in systematic reviews and meta-analyses, and there is a keyword small study effects coined by Jonathan Stern a few years before, and they are of very difficult sources here. So most well-known word here is publication bias. Publication bias, there's much evidence of publication bias, and this means that often small studies tend to be published only if they show a large effect. So if they show no effect or effect in the wrong direction, they might be not published. And there's also another form related to this, and that's selective outcome reporting bias. And this means that instead of reporting the planned primary outcome, when that is not significant, a secondary outcome may be reported that shows a better result. And there are also other related types of bias, and many words for these. So the general word is reporting bias, or also dissemination bias. And a few types of these are that there's evidence that studies having significant results tend to be published in higher ranking English language journals, while other studies having not significant results may be reported in national journals, national language journals. And this is called language bias. Then there's time lag bias, that studies with a fine, significant result may be published faster. And they even might be published more than once. That's multiple publication bias. And then there's also evidence that studies with significant results are cited more often than studies without a significant result, and they therefore are more easily detectable in literature searches. So why is that a problem? The problem is that if some trials with negative effects are not published, there's of course an overestimation of the treatment effects in the meta-analysis that have not found these studies. And therefore we have a bias here. Now we think that these biases are often related to the size of the study. Therefore this term small study effects. Because if a study is very large, it's very probable that it will be published independently of the result, because there are so many people involved, and they must publish the study independent of the result. But if the study is very small, the investigator may lose his interest of the study and might not publish it. So therefore, these problems with the bias are related to the size of the study, and they tend to be more often for the small studies. And if now we have such a small study effect, this means that smaller studies we have found may have bigger effects than the large studies we have found. So we are investigator of a systematic review, we do our literature search and find studies, and often we see that the small studies have the bigger effects. So this may be due to publication bias or to selective outcome reporting bias, as explained before. There's also another bias related to this called selective analysis reporting bias. So instead of the planned analysis, an alternative analysis method may be reported that shows a better result. So take simply another test also. But there are also other reasons not related to bias. So the smaller studies might also have different patients than the greater studies. So there might be clinical heterogeneity between the patients in the large and the small trials. And for binary data, there's also a statistical correlation between the treatment effect estimate and its variance simply by definition, because the definitions use the same entries of the 2x2 tables, and so they are correlated completely independent of bias. And finally, there might be simply coincidence, so that small studies simply by coincidence might show other effects. Now we want to look at this, we want to do a visualization of this, and the funnel plot is the graphical representation of the small study effects. So this is funnel plot. We have the treatment effect here measured as an odds ratio on the x scale in the logarithmic scale here, and some measure of precision at the vertical scale. And measure of precision taken here in this fiction example. Sorry. Yes. No. Yes. So the measure of precision here is the inverse of the standard error. Often you see the inverse variance, or simply the sample size of the study, and or the standard error, but in a reverse scale. So we have some measure of precision. So at the top of the plot, there are the large studies, and at the bottom of the plot, there are the small studies. And for statistical reasons, it is clear that these large studies have smaller standard error or higher precision. So the estimates for these are very precise. And at the bottom of the plot, there are the small studies with, which maybe have larger differences to the mean effect. So the funnel plot will look like a triangle ideally. So, but if there is a small study effect, this means that the funnel plot may have another shape. Now we first have a look at the pooled estimate, and this might be this here for all studies seen here. But now, if maybe odds ratios smaller than 1 mean a positive treatment effect, and odds ratios larger than 1, so on the left-hand side of the plot, might show negative results. So there might be a tendency to not publish these effects on the right-hand side of the plot. And this is looking like this here. No, this is here. So now they are outgrade here. Some of these points, so that I step back. So that was the funnel plot, and now there are some points missing on the right-hand side of the plot. So these represent the small studies not published and therefore not found in the literature search. And now the funnel plot has another shape. It's no more symmetric, no more triangle form, but it's asymmetric. So we see asymmetry in the funnel plot. And this can be seen visually, and it can be tested, of course, with statistical tests. And the bias seen here, when we reduce the studies only to the studies we have seen now, so when we skip these white studies from our analysis, the pooled estimate goes to the left, of course, and that's the difference of these two estimates represents the small study bias or publication bias for this example. So if we don't see these studies at all, then we have a bias in the meta-analysis and we have asymmetry in the funnel plot. This is how a funnel plot is defined. I've said some words with this before, and it is preferred to use the standard error on a reversed axis for the vertical axis, because then confidence intervals are increasing linearly, and there's also sufficient space for the imprecise small studies to be seen on the plot. This is how we can do a funnel plot using R. This is an example, the Olkin data, which is part of the R package meta. And you can do a binary meta-analysis called here M1, defined in the usual way. We have seen this before. There are the event numbers coded here as event point E and event n point E for the experimental group and point C for the control group. And as an effect measure, we take the odds ratio here. And if this meta-analysis is called M1, this object, then we can do a funnel plot by simply using the funnel function of the meta package. And this is an example, just this example of these Olkin data, meta-analysis of thrombolytic therapy with very, very many studies, 70 studies here. And this is sort of a triangle, but we might see a gap at the left, at the right bottom part of the plot. There might be a gap where we could think of missing studies right there. This is another example for another Cochrane review, post-operative vomiting, and there might be some asymmetry too, but we don't know. So I think it's not so easy to interpret this funnel plot. So what we see here is that visualization is maybe not all what we should do. We should do some statistical analysis for this too. And this is a third very famous example, the magnesium therapy example, cited in very many papers and also books and the Cochrane handbook. And there's very, very much asymmetry here. There are almost no studies on the right-hand side of the plot. And we have also much heterogeneity because we see some studies to the left of this big triangle here. So they have very, there are outlying studies in the sense of heterogeneity here. And this is a very interesting example because we also see a very, very big difference. I don't know whether you see this there or maybe in your paper handouts. There's a big, big difference between the random effects and the fixed effects estimate in this case. So that's a case of heterogeneity, maybe caused by a small study effect, maybe caused additionally by other reasons, and it's a meta-analysis you have much to think about. So, small study effects, tests for small study effects are so-called funnel plot-based tests. The first one and most famous one is the test by Matthias Egger. And there are others, I will give a list soon, but I have to say beforehand that they are criticized by some authors, mostly John Ioannidis and co-authors. They are very, very critical about funnel plot tests and have developed other tests, so the so-called excess significance tests, which are quite different. Then there's also, so what is a test? We could test for small study effects, but that then might be the test is significant and then we know there is a small study effect. And then we are a bit lost because our estimate we know is biased then, and we have no better estimate. So we have, we want to also adjust our estimate for this bias, because we want to have an unbiased estimate. So therefore, sorry, I always have this. Yeah, we have to we want to adjust for the bias, and there are some adjusting methods proposed in the literature, and one of the oldest is the so-called trim and fill method, and I will say some words to this, and it's also in the practical. Another method is the so-called Copers selection model, proposed by John Copers in a list of a couple of papers, which is more principled than the trim and fill method, but also more advanced, it's a more advanced method and also more difficult to conduct. And there are methods called adjustment by regression, and there's also an idea by John Copers, and the first who did this systematically was Tom Stanley, and there are some papers by Santiago Moreno and Alex Sutton, and also papers by ourselves. So the common aim for the funnel plot test is to have a test for association between the treatment effect and the standard error as an indication for asymmetry or small study effects on the funnel plot. The common assumption of these tests is that under the null hypothesis, there's no association between the treatment effect and the standard error if there's no small study effect, that there is simply no asymmetry. And all these tests have in common that they are strictly valid only for normal distributed outcomes. And they are often nevertheless used for binary outcomes because binary outcomes are very frequent. But they are not valid for these. So we have, this is again the funnel plot. We have seen the slide before. And the idea of some of the first tests here, this is the test by Begg, is in this plot, because of this asymmetry, we see a correlation between the estimated treatment effect and the estimated variance. And these tests are based on testing whether there is a correlation like this. So this is a list of tests existing here. There are rank correlation tests. The first one was the test by Begg and Mazumdar, and this was modified by Guido Schwarzer in 2007 for binary data because of this natural correlation between the treatment effect and the variance estimate for the binary data. And the other kind of test is regression tests. The first one was the test by Egger, and then several people acknowledged that this is not valid for binary data, and again the Egger test was modified by at least 4 authors. There's a test by Roger Harbord, a test by Peter McAskill, a test by James Peters, and also a test I have developed. And this is a very large list, and of course I cannot tell you now the details of all these tests. So I simply mentioned here, but in the appendix of your handout you might find the exact definitions, and there's also a reference to an overview by Jonathan Stern and co-authors where these tests are explained in more detail. The basic idea of the Egger test and of all the other tests I have mentioned here is the following. We choose some effect measure, say a log odds ratio, and theta I hat be the effect estimate of study I, and SE of theta I hat the estimated standard error, and the null hypothesis means the treatment effect is not depending on the precision, and the idea here is to regress the treatment effect theta hat on the standard error with study weights in the usual way as inverse variance weights. So the same variance, the same weights you use for the fixed effect model. And then to test the null hypothesis of a zero slope here. This is exactly the idea of the funnel plot. If the funnel plot would be symmetric, this slope would be 0. And if the funnel plot has some direction not parallel to the vertical axis, there is a non-zero slope. And this is tested here. And again, I hint to the problem with the binary data. The log odds ratio and its variance estimate are not independent by definition. So you often will find a slope here as a false positive result of funnel plot testing. And all the other tests have the same basic idea, but they use in detail other estimators and so on. These are these tests. So the Harbord's test is a score test, uses a score-based estimate for the odds ratio instead of the Wald estimate. so that the variance estimate depends only on the marginal totals, which might fix the problem. The Peters test uses the usual odds ratio estimate, but then simply the inverse sample size as regressor, which is of course independent then. And the same idea is at the bottom of the arcsign test. We don't use the log odds ratio here, but the arcsign difference, which has 1 over n as its natural variance estimate. And so the variance again depends only on the group sample sizes. So that are the basic ideas of this modified tests. And now how to perform a funnel plot test in R. That's very easy again. You have a meta-analysis, that is this data we have used a few minutes before. And the function in the meta package doing funnel plot tests is called meta bias. So, and you get Egger test if you take, is this the Egger test or? No, this is, you have changed the default, have you? Yes. So if you use this in a default way, then you get the Harbor tests, or efficient score test here. So if you want to have other versions, there is an argument you can change which method you want to use. You can also use the Egger test or the Peters test or one of the other tests. And if you look at the result, we find a t-value and a p-value, and the p-value is 0.087 something. And this means that there is a hint to asymmetry in the funnel plot, because the test level used in these funnel plot tests is always 0.1, because we are somewhat liberal here, because the problem is that we have, if the null hypothesis of no bias is true, that we have no problem, but we want to know if there is any bias. So therefore the test is liberal, and in this sense the p-value is less than 0.1, and therefore there is some hint to asymmetry or maybe publication bias in this data here. So this is a list for a table of the results of the different tests for this and the other two examples. So for the first example, this was the Olkin data. We have seen just the Harvard score test result, 0.09, and we see the results of the other tests are very similar to this, with one exception, and this is Guido Schwarzer's test, which is not significant here. So I would say there is some hint to certain asymmetry here, if I look at these 6 tests here. The second example, Granizetron, there is, the results are very different. Most tests see no bias here, but the Egger test is has a very significant p-value here, but this may due to the problem with binary data the Egger test has. So I would say this is a false positive result, and also for the Peters test. And the third example, magnesium, most tests show that there is a very, very large bias, but the rank correlation tests, Beck and Schwarzer, are not sensitive for this, it seems. So this might be a problem with these tests. So there are many interpretations of this, of course, so the problem might not be solved, but we have many tests and we have many results, and we have a look at the funnel plot, so it's not that easy. Yes?
If you go one slide back to the different tests and the different data sets, in the first 20, yeah, it's 17 in our, but here it's 22, I believe, in your...
Yes, this one?
This one, yeah.
Mm-hmm.
So could you explain very well why you believe that certain tests are false positives in Granizetron and magnesium test, So why is Schwarz's test different than the others in the Olking
I think
data set?
if there is some evidence in the literature coming from simulations that the rank correlation tests, these are the Beck test and the Schwarzer test, have very low power. And if the tests have very low power, so look at the magnesium example. This observation would completely explain this, what we see here. So if these tests have low power, they don't find asymmetry in this plot, but the others do. So if I would trust the others test more than the rank correlation test for this example, because they all show very large asymmetry, and having low power is a good explanation that the tests simply don't see this.
To complement what Goethe says, the rank tests will have less power if there's a smaller number of studies, because they're rank tests. They don't actually capture the extent. So what you see with the magnesium plot is there is a very strong slope, but relatively few studies, and that's why these rank tests don't have so much power here as well. The only other comment I guess we would make is that the tests that we've worked on explicitly try and model the heterogeneity in the funnel plot alongside the slope with the standard error, or 1 over the standard error. And so if there's a lot of heterogeneity, some tests can get confused. So I think this is what's happening in the middle example here. The Granistron example, the Harvard score test here doesn't handle this additional heterogeneity very well. So it can't pick up, the Peters test doesn't handle this asymmetry very well, and so it gets a bit confused, so it's a bit significant. And Egger's test here also. And the other thing, as Goethe was saying with these tests, is that you get an inbuilt association between standard error and estimate when you've got binary data. And unless you take account of that in your modeling, your testing, you can mislead yourself. And the arcsign test is particularly designed to do that, and the Harvard score test is better at doing that as well. Is that
I think yes.
Yeah, is that helpful? So I don't know if Goethe was going to say this, so I'm sorry if you're going to say this, but if you go to the Cochrane Handbook online, then there is some guidance very similar to what we've got here that tells you which tests to use and when. And there's also this paper that we were involved with in the BMJ, which I think is
quite similar. So I think the recommendation paper chapter in the Cochrane Handbook is chapter 10, might be, and there's also a paper I will cite in a minute. So this.
Anyone else got any questions at this point? Yeah.
Sorry. It is not totally clear for me how you set up this funnel plot, in the sense, what is the center line, let's say? Is the estimate that you get from the meta-analysis?
Yes, the central line is, I will show the funnel plot again, maybe this year. No. in this, yes, here the central line is simply the 1, so the neutral line in this funnel plot. But in the other funnel plots, we go for the, yes, these are the data, and here the central line, or take this here, the central line is the fixed effects estimate.
So you expect to have this sort of triangle around this estimate based on the fixed effects?
Yes.
Because the other one, in a way, was confusing for me, because how can you have that estimate having only studies on the left-hand side?
You mean that fictional example, the first.
You mean the ISIS-4, the magnesium example, don't you?
No,
No, I
if you
think-
go.
You mean this here?
one?
Yes.
Yes.
So yes, I forgot to say this, or maybe I didn't see it myself. So here, I think the one, or was it from the? Yes, this is simply the one, the neutral line in this example. So it's different in the examples. I'm sorry. And that was confusing you, of course. I understand. So for this, this is a fictional example to explain what a funnel plot is, and here the one is simply at the middle of the plot for whatever reason. So it could be skipped simply.
So because we generated these data. And so we just put in not the fixed effect estimate, which is what you have to do if you've only got the observed data, but we actually put in the true value, which is 1 here. Yeah. So.
And I have another question. Shouldn't we expect in advance that there is a sort of correlation between the estimate that we got and the standard error of the various studies because we underweighted the studies with less precision?
No, we don't underweight them. We weight them. They have smaller weights, of course, but this is due to the pooled estimate being the maximum likelihood estimate, and so they must be underweighted, because otherwise it would be biased.
But we expect more variability in the smaller studies, and so we give them less weight in the summary. But we don't expect them to systematically show a smaller or larger effect once you've accounted for the fact that they are more variable.
Okay.
So in other words, all things being equal, then the effects, the underlying true effect should not, that we're trying to detect with each study, should not depend on the actual size of that study. Does that help?
Yeah. So, in a way, the assumption is that you assume that are mainly the small studies that could suffer this publication bias because the larger studies are expected to be
anyway,
published.
So this is the common assumption for all these funnel plot tests.
Okay.
And, what I said at the beginning was that there are also statisticians who question this assumption and say, let's try other types of tests. And this idea by Ioannidis and Trikalinos is to look for so-called excess significance. So they count how many results in the meta-analysis are significant and have some ideas to, how to test whether these significant tests are too many. And this is another idea completely independent of small or large. So these are other tests, but not based on the funnel plot or on these small study effects, but based on simply a complete different idea. So there are other things I have skipped here, but I want to mention them. Okay. There's a quite recent paper by Ioannidis in the, I forgot the journal, in some journal, from 2014. Maybe published online or even open source. I could give the years. It's not in this literature because it's so new, but there is some. It's a sort of overview.
Thank you.
Yes. Now these are the recommendations mentioned before on testing for funnel plot asymmetry in a paper by 19 authors, including the three of us. And they say, use tests for funnel plot asymmetry only when there are at least 10 studies, because it's a regression and we should have some data for these. So at least 10, that's a rule of thumb. We should not use tests for funnel plot asymmetry if all studies are of similar sizes, because then there is no funnel plot but a line. So if you have simply all studies are similar size or have similar standard error, these tests are not sensible. Use linear regression tests only those which have larger power than the rank correlation tests. So the regression based tests are, linear regression-based tests are preferred. And then, of course, because the power is low for all these tests, bias cannot be excluded if the test is not significant. And heterogeneity is always a problem. So if you have large heterogeneity, you may not even expect that the funnel plot has a triangle form. So the test performance deteriorates greatly if the between-study heterogeneity increases. For continuous outcomes, the Egger test is recommended, but for binary outcomes, and if the heterogeneity is not too much substantial, these modifications are recommended. And if there is heterogeneity, one of these arc-sign tests, there are 3 proposals in detail, is maybe, I don't know, is recommended at least in this paper. So the last point for this session is adjusting for small study effects. There are 3 approaches. I have mentioned them, the trim and fill method. The idea here is to add the missing studies formally to the funnel plot until it becomes symmetric and then do the meta-analysis. The Cooper selection model is this principled approach. It's a special case of the 2-stage Heckman model used in economics. And it models the treatment effect and the selections simultaneously in a model. And the regression methods use the idea of the Egger test and do a weighted regression based on the funnel plot, and then uses the slope of the regression line for estimating a corrected treatment effect. So now, first, the trim and fill method. This is a visualization simply of the idea with some example. This is a funnel plot which is not symmetric, we would say, if we look at this. And the idea now is to identify, in the first step, outlier studies. So there's a procedure identifying outlier studies, and they are grayed out now. So these are the outlier studies, and the central studies at the top are the not outlying studies. And now a meta-analysis is done for getting a pooled effect only from these 4 studies. Now the rest of the 4 studies not outgrayed here. This is this symmetry axis here. I don't know whether it cannot be seen very well. Okay, there's a symmetry axis, and now the studies revive again, but are mirrored. Get all them of these outlier studies now get mirror images on the right-hand side of the symmetry axis. So these are in white here, so open circles. And now the funnel plot looks a bit more symmetric, and finally there's a random effects meta-analysis done on this new study set with the added studies, the filled-in studies, and here's a fixed and a random effects estimate given here, and this is serves now as the corrected estimate for this meta-analysis. Yes, this is a trim and fill method simply visualized. The second is the Cooper's, yes? Finish. Okay, should we skip the rest, or because of time, the problem is we are running out of time.
Well, can you just give a very brief overview? Maybe?
So there are not very many slides now. So the Cooper selection model is the most complex of these models. I will skip the model slide. That's the next one, of course. Yes, that's not the model slide. So yes, that might be of interest because there is a hint to the package. So the Cooper selection model is very complex, but it is possible to do it in R using the meta sense package Guido Schwarzer has mentioned before. And you will find in this, there's a reference by James Carpenter and other 2 of us giving showing how we have realized this in R. And the last method, adjustment by regression, is also realized there. So I will skip this slide because it's very technical. And have a look through this example. This is the same example you find in the practical for this session. And meta-analysis of 37 trials. And we have simply a look, a visualization, a graphical look at what is done here. So these are the data. A very, very asymmetric plot for whatever reason. So that's surely no triangle here. So these are the estimates from the random effects model and the fixed effect model, and they are very different. You see that. And this is a hint to asymmetry and maybe bias. Now we add the trim and fill method estimate in black here and the Cooper selection model in yellow. Maybe you don't see this yellow estimate. It's the most on the left. So it's correcting very strongly. And you also see the filled-in studies by the trim and fill method here on the left-hand side of the plot. And lastly, the regression method estimates are also correcting this, and we have now a set of methods, we see a set of estimates which try to correct for the bias, but they are also very different because the methods differ, and the example maybe is somewhat extreme. And these are the numbers, same examples, different confidence intervals. You see very, very different estimates here. The random effects model surely overestimates here the effect, and the others maybe are somewhat more realistic. This is a summary plot for these methods. I think there's nothing new except that there is also for the regression adjustment method a function called limit meta implemented in the new R package MetaSense I have mentioned before. So this is a package for doing sensitivity analysis in case of biased meta-analyses. And this is a summary for the whole session. Yes, I think I can skip these words, or can I? Can I read them? It's better to have discussion if anyone wants to ask a question. Or yes.
In the case of this methodology that you mentioned, trim and mirror, no, this one, trim and fill, which standard error is attributed to the mirroring studies?
To the new studies, I think the same. For the mirror images, the same standard error as for their original studies.
So the effect at the end is not very far from simply deleting the outlier studies?
Maybe yes. This is, in fact, this is another suggestion made by Tom Stanley. He wrote a paper called, I don't know exactly the title, but it was, might it be better to discard 90% of the data? So he observed the same thing, so simply skipping the biased small studies would lead to this, might be to good estimates. So the question is, simply delete 90% of the data and you get a better estimate than if you use all data, if the data are biased. So this is maybe some
quite dangerous,
provoking title and paper, but it's interesting to think about this.
Yeah.
So
I think it is a bit against the principle
yes.
of the systematic review that aims in being comprehensive and covering as much as possible the existing evidence.
So
no?
if you think this small study idea to the end, then you come up with don't trust the small studies.
Yeah. On the other side,
might be it's somewhat provoking and might be wrong.
Could take a different perspective and saying that these, let's say, outlier studies are those that are really bringing in an interesting information, because it is not necessarily corresponding to the average,
Yeah.
no? And maybe are those that require really
Yeah,
major
maybe
attention.
they represent simply clinical heterogeneity between patients, and if the reason for the asymmetry is not bias but a true clinical heterogeneity, then it would be, of course, wrong to discard studies. So it's not so easy, I think.
So if you go back a couple of slides, Geertje, to the different methods, so we all published a paper in the Journal of Clinical Epidemiology on looking at a large number of meta-analyses, and we compared trim and fill and the COPAS model, and we found that the COPAS model was more appropriate in general. And then so I just thought about it a little bit more, the relationship between the regression studies and the COPAS model in the run-up to this workshop. And I think that actually, in many cases, they will provide very similar results. So the adjustment by regression is probably a very natural first step to do if you're concerned about publication bias, and that's computationally very simple. And it basically is broadly going to give you the right answer if the reason for the selection depends on something that's captured by the standard error, but doesn't additionally depend on the actual underlying effect size beyond that. And we'll see some of these in the practical. Trim and fill is a very nice graphical approach, but it rests on quite strong assumptions, which the ones you've highlighted, that you're putting in these extra studies. You're assuming that the extra studies mirror the ones both in the terms of point estimate, but also in the terms of the precision as well. So.
Okay, so
Any more questions at this point? So we can try doing this stuff in R now, and our suggestion is that you continue on with the practical materials from wherever you'd got up to, because then you'll be able to build on your knowledge.